Annyeonghaseyo and greetings, 8th graders. Thank you for attending our live session on Tuesday. Forgetting what day it is. Distance learning has got me losing my mind. Anyways, thank you for attending the live session today. I thought it went really well. Hopefully you were able to understand what Mr. O was explaining about phase change and pressure and the reason why we've got ice in the mantle even though the mantle is very hot. Just if you understand that the mantle holds ice and if you understand that even though it's hot, water is in the form of ice because there's so much pressure. That's all you need to know. That's all you need to know for today. So don't worry too much about a lot of that other information that came out of the lecture. Mr. O he's got a passion for chemistry, and when you get him started on phase changes, that guy's a savage. So anyways, hopefully the review session was helpful for you all. Today we are going to talk about mass extinctions. So our objectives for today is to understand how the evidence for mass extinctions can be found in the fossil record, and then our language objective is to be able to explain how we can find evidence for mass extinctions in the fossil record. We've got a lot of keywords today, so please follow along. Our first keyword is strata. Now strata is something that I talked about in our last slide, and strata is simply a layer of sediment from the same time period. And one thing that I should clarify about strata is strata is going to be different in different places. So strata in the ocean is going to be different than strata in a riverbed, but if they're from the same time period, they're the same strata. The way we can tell that two different types of sediments are from the same time period are by looking at what's fossilized in those strata. We can find organisms that exist in certain time periods and not in others, and that lets us know that strata is from a certain time period. We'll go over this more as we go on, so don't worry too much about the definition of strata. I just went over it once. We'll go over it again later. Next, superposition. We'll talk about this later as well. Mass extinction. All of you should know what an extinction is. An extinction is when every single animal in a species dies and it no longer exists. So for example, there used to be a form of human that was around called a Neanderthal, and Neanderthals, they don't exist anymore. They're not alive. They died out. Some of them interbred with humans, and so their genes are kind of carried on with us, but there are no distinct Neanderthals that exist today. The same can be said of animals like saber-toothed tigers, woolly mammoths, and dinosaurs. All of those animals went extinct. Now, when we talk about mass extinctions, we're talking about the death of not just one or two species like woolly mammoths, saber-tooths, Neanderthals. We're talking about the death of almost all life on Earth. So there have been 5 different time periods on Earth where almost all life has stopped existing, and that's called a mass extinction. Our next keyword is from our astronomy class, gamma ray burst. If you remember, a gamma ray burst happens when a gigantic star explodes, and it's spinning so fast that it channels all of its energy into 2 beams that shoot out from that supernova explosion. And so gamma ray bursts can be very destructive. They can cause mass extinctions, and hopefully you can put 2 and 2 together and make a guess about how gamma ray bursts are going to be a part of today's lecture. Our next 2 words are also from our unit on astronomy. The first being comet, which is just a ball of rock and ice and dust that kind of circles or orbits the sun from the Oort cloud. And so different comets have different orbital periods. Halley's Comet, I think, has like a 75-year orbital period. So when I was in, I don't know, 4th grade, 3rd grade, Halley's Comet came, and that was a really big event, and people were really excited about it. I probably won't live long enough to see Halley's Comet come back, but maybe you will be, let me think, 86, 2016, I don't know, you'll be old. You'll be old when Halley's Comet comes back. Our next word is asteroid. Asteroid is just a space rock. And then finally, our final keyword is iridium. Iridium is a radioactive substance, much more common in space than it is here on Earth. Okay, so let's dive into our lesson today. Let's talk about rock layers and the fossil record. As I mentioned before, rock layers are deposited kind of chronologically, right? So we have sediments built on top of sediments, built on top of sediments. And so this is the law of superposition. The law of superposition sounds really fancy, but really it just means that the deeper that you go into a group of sediments, the further back you're going to go into time. And so sediment is deposited from the bottom up. And here we've got a very crude example, but still I think it's a really great example. And in picture number 1, we have an image of probably early Earth. As many of you know, life began in the oceans on Earth before it ever ventured out on land. And life existed in the ocean for, off the top of my head, I would say close to 1 billion years before it ever got onto land. And maybe that number is wrong, maybe it's like 500 million years. But nonetheless, it took a very long time before life ventured out of the ocean onto land. And so things that were living in the ocean a long time ago, we'll say fish, they would have died and fossilized, and they would have been in these deeper layers of strata before life ever made it out into land. And that's picture number 2. We've got life makes it out onto land, and we'll just say that's a dinosaur, right? And so dinosaurs are located in a strata that's higher than older creatures like ancient fish, the very first fish. And then picture number 3, we've got a monkey, which we'll say stands for mammals, which appeared much later than dinosaurs. There were early proto-mammals that existed with dinosaurs, but in general, like things like monkeys, right, appeared after the dinosaurs. So that would represent another layer in the fossil record. And so I'm sorry that this window is superimposed in the corner, but just to read it to you, it says, so the deeper that you go, the further back in time you are. Okay, so the deeper that you dig, the further back in time you go. And so monkeys would be the most recent, dinosaurs would be even older, and primitive or early forms of fish would be some of the oldest fossils that you would find. So this is the law of superposition. Next, the rock layers are divided into like 3 very broad periods, Cenozoic, Mesozoic, and Paleozoic eras. So the Cenozoic era is our most recent era. This is the era of mammals. Things like woolly mammoths, saber-toothed tigers, these existed in the Cenozoic era. If we go further back than that, we're basically talking about the age of dinosaurs. To go back still even further, we're talking about early life. Mostly we're talking about life that was in the oceans before it crawled out on land, but we also have some of the earliest forms of life that did come out on land, like amphibians and some of the first reptiles from the Paleozoic era. So as I mentioned before, when we talk about strata is going to look different in different places, right? You're going to have different types of sediment in a river compared to an ocean, compared to a landslide. So the way that we identify a strata is not through the composition of the sediments, but it's actually through what kind of fossils that we can find in the sediments. So an example that I'm going to give to you is a trilobite. So trilobites, they are creatures that look like this. When you hear the word fossil, a lot of times you'll see images of a trilobite because trilobites are so common. They're such common fossils. They're also just kind of a really good example of a fossil because it's something that we'll never mistake for a living thing because trilobites don't exist anymore. Trilobites existed in the Permian era about 252 million years ago. So if you are digging for fossils and you find a trilobite, then you know that you are at least in a layer that's 252 million years old, if not older. If you are looking for trilobites, or if you're looking for, I would say, more recent forms of life and you find trilobites, you've gone too far. So just keep this in mind. Index fossils are one way that we identify strata. Now, we talked about the law of superposition, and the law of superposition, of course, has some exceptions. This is because the Earth's crust is constantly moving. So typically, layers of sediment are deposited on top of each other, one after another. But also, we have tectonic plates that are moving around, right? So we talked about convergent boundaries yesterday when we did our review. So we have one plate moving over top of another plate, right? And this is oftentimes not a smooth transition of one going under one plate subducting under another plate. Usually it's kind of violent. There's a lot of friction there because they're plates of crust, right? They're gigantic rock plates of Earth. And so there's earthquakes and gradual movement. A lot of times at subduction plates you have mountains that come up. For example, the Himalayan mountains, where the Indian plate meets with the Eurasian plate, that's the Himalaya mountains, and that's created by subduction. And so in those areas, a lot of times you'll have crumpling of the Earth. And here's a picture that I feel really illustrates that fantastically. Earth is literally getting crumpled up. The crust is literally getting crumpled up because these two plates are pushing into each other with so much force. And that red line is where the fault is, where the two plates are. And so this isn't a very clean fault line where one plate is clearly subducting against another. They're just kind of pushing against each other and they're crumpling. Perhaps they're going to push a mountain range up, and eventually maybe there'll be an earthquake which will force one plate under the other. Next, the fossil record sometimes has some abnormalities, and let's talk about this. So sometimes when you're looking for fossils, you'll find an empty space that has no fossils. And then when you're looking past that empty space, you'll find new and different fossils from what was before the empty space. Okay, and so let's talk about these empty spaces, because these empty spaces are super important. They really tell important stories about what's happening with life. And let's look at our picture here too, right? So with our picture on the left, we see if we go really, really deep, right, we see all kinds of different creatures, different organisms that are in the fossil record. And then there's that red line, and that red line shows us a place where we don't find any fossils. And then once we look above that red line, we're seeing some things, like a few things from what was below the red line, but not a lot. Okay, and this represents, of course, a mass extinction. And so if we looked at this red line and we found traces of meteors in that red line, then what do you think that would indicate? Probably that a meteor caused a mass extinction. If we looked at that red line and we found volcanic ash in that area, we could assume that, oh, maybe volcanoes caused a mass extinction. If tropical plants suddenly appeared, we could guess that, oh, perhaps climate change. The world got warmer and climate change was a part of a mass extinction. So these are ways that we can read the fossil record, and we can understand what's happening in the fossil record, what's happening in the history of planet Earth. And hopefully you can think back to our statement of inquiry, which is the story of the Earth is written in rocks. Okay, so we're going to talk about two mass extinctions as we wrap up our class for today. So the first is the Ordovician-Silurian extinction. And at this time, almost all life was in oceans. It was in the ocean. 70% of all living species died. And it was caused by the cooling of the atmosphere, glaciers, and possibly a gamma ray burst. So this is an image of some Ordovician life. This is what the Earth looked like back then. Very different than it is now. Here's a picture of, oh, actually I've got these in the wrong order. Gamma ray burst, and next is a picture of glaciers and of a frozen Earth. Now, I talked about this briefly during our unit on astronomy, but more and more the evidence for a gamma ray burst is increasing, and let me explain why. So if this was an extinction that was caused by global cooling, then we would have lots of evidence of glaciers of glaciers first and then animals dying off later. But in fact, what the fossil record shows is that animals died off very quickly, and then very slowly these glaciers came in. And so the way that gamma ray bursts happen is that they destroy the ozone layer, and the ozone protects life from ultraviolet radiation, and that ultraviolet radiation ultimately started killing life. In addition, gamma ray bursts will destroy the atmosphere. They'll destroy the atmosphere's ability to hold on to heat, and so because they create chemicals which sort of destroy greenhouse gases, to make a long story short, anyways, the Earth gets cooler, and so we had a sudden die-off of life, followed by a gradual cooling of the planet, eventually cooling so much that we had what we call snowball Earth. So the next extinction event I want to talk about is probably the most famous mass extinction that there is. This is the Cretaceous Tertiary extinction, also known as the KT extinction. I believe it's called the KT extinction because there was a German scientist who hypothesized about it. Anyways, in Germany, I guess they use K instead of C for Cretaceous, so KT extinction means Cretaceous Tertiary extinction. Not only did this extinction wipe out all the non-avian dinosaurs, but 75% of all species were wiped out. First of all, the term non-avian dinosaurs maybe doesn't make a lot of sense to you, but basically there are still dinosaurs that are alive today. The living dinosaurs that exist today are the birds. Everything but the birds were wiped out when the Cretaceous Tertiary extinction happened. In addition to dinosaurs getting eliminated, 75% of all species were wiped out. Generally speaking, basically everything that was big got wiped out. Very small living things survived, including these mice-like animals, which were sort of the ancestors of modern mammals. So if we look in the fossil record, we can see kind of like a layer of empty sediment, which indicates the KT boundary. In this rock, I'll go ahead and just maybe make a little red line to show this is what they call the KT boundary. This is kind of the empty space in the fossil record that they find all over the world. Like I said, sediments are different in different areas. You've got river sediment, you've got ocean sediment, but you have the same kind of fossils from the same period in those sediments. However, those fossils stop at a certain point, and there's an area where there's almost no fossils. And then in the higher layers of sediment, you'll find less fossils and gradually increasing and gradually changing. So that KT boundary is really important. We can also see it here in this, I guess, image of like a hillside that has either been eroded away, or perhaps there's some construction where they cut through and made a road. Anyways, we can see that dark band, which is the KT boundary. Now, not all dark bands represent extinction events, but if you look closely at the fossils which are in that line, then that lets you know that there was an extinction event that happened. And as many of you know, people think that this event happened because an asteroid or a comet crashed into Earth somewhere near the Yucatan Peninsula of today. And so that those concentric circles show maybe the impact area of that asteroid. And this is an image of what it would have looked like as it crashed into Earth. One interesting thing is that they can find iridium in this sort of KT boundary. Now, iridium is an element that is common in space, but not so common on Earth. When the Earth formed, most of the iridium sunk down towards the core, so we can't really find it a lot on Earth. But there is a unexplained abundance of iridium at the KT boundary, and lots of people think that this is there because it shows that a comet crashed into Earth or an asteroid crashed into Earth and wiped out life as we know it. So your homework for today, I'm sorry it's a little bit longer class, a lot of information. Hopefully you're able to keep up. Your homework is going to be a little bit challenging too, but I think it'll be interesting. So we are probably in the beginnings of the sixth mass extinction. 1 million years in the future, what do you think will be found in the fossil record? So write 5 to 8 sentences, about a paragraph about what's going to be found. And just imagine that the people who are looking at fossils 1 million years in the future, they don't have access to books or, I don't know, computers or, internet records to know what exactly happened. They've got to figure out what happened based on the fossil record. So what are those people going to find in the fossil record which lets them know about the sixth mass extinction? If you have any questions, as always, hit me up at sjkwok@sejongacademy.org. You can also contact Mr. O at hoh1@sejongacademy.org. And I have office hours every day from 9:30 a.m. to 10:30 a.m. Okay, thank you. Peace.